Yeah. Okay, I would like to welcome you at this session, Floods and Droughts, Predicting and Assessing the Risks. First of all, I would like to thank all those people that have participated in the preliminary phase to this conference, in the discussions we had on the platform, on the web platform. And I believe we got very interesting questions from the people that participated, especially from the aid community, so the people that are on the ground in developing countries dealing with risks and that have to find solutions on the spot. And yeah, some faces here are familiar. I've met them on the virtually on this platform. So what we are addressing here is how we can use models, tools, data to predict and assess risks related to floods and droughts. These are both two water resources problems. One is the extreme wet end and one extreme dry end of the hydrological cycle. Then, excuse me. Floods, generally when we think about floods, we think about structural measures. Structural measures are dams, are dikes, are levees, are flood barriers that are built or that have been built and that should give shelter and protect people or countries from floods. The same can be said for droughts. There are droughts, or in the case of water absence, we use infrastructures such as dams, as reservoirs, where we can store water that can be released in case it is needed for irrigation or drinking water purposes. But in many countries, this type of infrastructures are very expensive. They cannot just be built fast. They need huge capital investments. And therefore, it is better, or we have to look for solutions in which we can use non-structural measures to help people to protect property, to get into safety, and to get out of danger. And these tools are basically spatial planning. They are forecasting. By forecasting, they are integrating weather forecasts, so outputs of weather models with hydrological models and hydraulic models to predict discharges and stages on a river or, for instance, on a coastline. After that, we have to issue a warning to the community, and then people have to be moved out in safe areas. And this can only happen if there is a structure in place, if institutional issues are addressed, if there is a certain organization there that allows people to seek safe areas. Now, technology has advanced in the recent years. Data that were unimaginable before, such as online satellite data, digital terrain models, satellite observations of water levels have become available, and they allow us to set up warning systems and models and advance the prediction and forecasting process. And one scope of this session is to show how we can integrate models with data to produce forecasts and to disseminate them, and therefore to assess risks ahead of time. Now I would like to invite, we have invited four panelists. I starting in the row of, in the line of, in the sequence in which the presentations will be held. One is Tom Graziano, from the Chief of the Hydrological Services Division of the US National Weather Service. He will give us a presentation about freshwater prediction and flood warning services. The second speaker is Rafael Oreamuno from the University of Costa Rica. He will talk about challenges in flood forecasting in his own country in Central America. Third speaker is Professor Ezio Todini. He's from the University of Bologna, and he will talk to us about an important aspect, which is uncertainty in forecasting. The last speaker is Rowan Douglas from Willis Reinsurance Company, and he will talk about insurance aspects related to floods. Now I would like to invite the speakers to come forward. Thank you very much.
Thank you, Paolo, and good afternoon, everyone. As Paolo mentioned, my name is Tom Graziano. I'm Chief of the Hydrologic Services Division with the National Weather Service. And today I'm going to talk a little bit about what we do, our infrastructure, how we provide services, how we plan to enhance those services, particularly with regard to improving our products and services and enhancing the communication of risk. I'll talk a little bit about our mission, the impacts of floods, essentially the impetus for all the activities that are underway in our agency, how we deliver services, how we're modernizing services through an initiative called the Advanced Hydrologic Prediction Service. I'll show you some examples of new products and services, talk a little bit about flood inundation mapping, which is a heavily partnered activity with other federal and state and local agencies in this country, particularly FEMA, the United States Geological Survey, the Army Corps of Engineers, others. And I'll end it with talking a little bit about expanding our services into the water resources realm. I think we all probably heard about, at least in this country, we've talked about water being the new oil, about sort of a looming water crisis 10 or 15 years down the road. Scarcity of water, the need for new and better information to support informed decision making, to assure that we have water for future generations. Our mission, as I mentioned, it's all about protecting lives and property, producing forecasts and warnings for the protection of life and property. There are many, many agencies in this country, federal agencies and others, that have some hand in water, in the water data collection, processing, integration, forecast. But the only agency in this country that is responsible for issuing warnings is the National Weather Service. So I'll talk a little bit about that. Why is this an issue? Why is it, what's the impetus for the work that we have underway? On average, over the past 20 years, the United States flooding has claimed over 90 lives and caused damages in excess of $7 billion. Floods occur in all 50 of the United States. No state is immune from the impacts of floods. Threats are all months of the year, and then more fatalities associated with floods than any other severe weather-related phenomena in this country. And interestingly enough, in this country, when you look at the deaths and the cause of flood-related deaths, more than half of the deaths in this country associated with people trying to drive their cars through water-covered roadways. And in response to that, we've initiated this campaign called "Turn Around, Don't Drown." Simple, a little catchy. I'll talk a little bit more about that later. Okay, our operational infrastructure. How are we built to deliver services? Weather Service is comprised of 6 regions. We have 9 national centers for environmental prediction, 3 of which are closely involved or heavily involved in the water forecasting business. We have 13 river forecast centers. Most people, even in America, you talk to them on the street and you ask them about the Weather Service and what it does. 99 out of 100 of them will tell you that they had no idea that the National Weather Service had anything to do with water forecasting. But it's a primary aspect of our mission. It's weather, water, and climate forecasts. And we have 13 rivers forecast centers which support that mission, 12 of which are in the CONUS United States, 1 of which is in Alaska. And we look at the river forecast centers as sort of the wholesalers of information. They run the models, they collect a lot of data, they produce river forecasts, which are then provided to our 122 weather forecast offices. And the weather forecast offices are essentially the retailers. They're open 24/7. They're constantly working with local emergency managers, state emergency managers, the media, et cetera, to try to get the word out about impending high impact weather and the associated threats and risk associated with those events. Just to round it out, we have 2 tsunami warning centers and 21 center weather support units. We also have a strong aviation presence in our organization. With regard to the National Centers for Environmental Prediction, there's three that have heavy involvement in the water forecast business. One is the Hydrometeorological Prediction Center. They're the unit based in Camp Springs, Maryland, just up the road, that on a routine basis, every 6 hours, provide national in scope quantitative precipitation forecasts, which are a critical input into our river forecast models. They also produce products that compare their forecast rainfall to the flash flood guidance, which is generated by our river forecast centers, to try to identify areas where at high risk for flash flooding. We've got a storm prediction center in Norman, Oklahoma, which produces heavy rain, mesoscale discussions, trying to identify areas where the rainfall rates are anticipated to be very high, where they're essentially on the order of more than a couple of inches per hour, so we can isolate areas which have at very high risk for flash flooding. And our climate prediction center, which is also in Camp Springs, Maryland, which provides short through extended range climate products which are incorporated into our river forecast, our extended range river forecast. I talked about the wholesalers, the river forecast centers. There's 13 of them. I'll go through this very quickly. They produce flash flood guidance, QPF information, multi-sensor precip analyses. They provide extended, short-range deterministic and extended-range probabilistic information, trying to convey the uncertainty or risk associated with the long-range forecast. I'll talk more about that in a minute. Weather forecast offices, they're the retailers. They're the ones who actually are sitting there, for the most part, talking to the local folks, the emergency managers, the media, trying to communicate the message, trying to alert people to the risk. They produce and provide an issue, the flash flood watches and warnings, and are the retailer, again, for the river forecasts and warnings. And very importantly, they provide the local outreach and education. When we talk about the forecast process, we talk about really three fundamental and equally important components. One is actually, observing, detecting, monitoring, forecasting, and warning. They actually getting the warning out. Two is communicating the warning. And three is response, to try to assure the appropriate response. We have to make sure that people understand the message, they understand the consequences associated, or the risk associated with that phenomenon, so they can take appropriate action. All three are equally important, and we treat them as such. How are we modernizing services? The Weather Service in this country back in the 90s went through what we call the modernization. It was we deployed new satellites, new Doppler radars all over the country, a new computational and communications infrastructure, a new surface observing system. A lot of infrastructure was put in place that we're leveraging now to enhance and modernize our water forecasting business. And what are we doing to try to modify or improve our forecast? One, we're now providing forecasts through the full spectrum, time spectrum, full range, from flash floods to seasonal freshwater forecasts, quantifying the forecast certainty to try to communicate the risk, providing more accurate and timely forecasts and warnings. We've seen over the past 20 years, particularly over the last 10, significant increases in our flash flood warning lead time and our accuracy. Lead times, back in the mid-90s, before the deployment of the Doppler radars, was on average around the country about 15 minutes. Last year we were close to 70 minutes, and the year before it's 77 minutes, the average lead time associated with the flash flood warnings that we issue. So the investment is beginning to pay off. Partnered flood forecast area mapping. I'm going to talk a little bit about inundation mapping, and this truly is a partnered activity among federal agencies, state agencies, and local communities, and talk a little bit about some of our visually oriented products. For many, many years, we talk about communicating information. You hear the old adage, a picture's worth 1,000 words. But we are always just in the business of providing text information, and that's a pretty limited way to communicate things. And now we've expanded significantly into providing, augmenting that text information with a whole, a slew of graphical products. How do you access this information? If you were to go to the Weather Service main page at weather.gov, you'd see the image over there on your left, which is just a threats map around the country for all types of threats, whether they be severe thunderstorms, tornadoes, red flag warnings for high probability or risk of forest fires, flooding, et cetera, et cetera. If you click on the tab there, as the arrow indicates, water, it'll pull up the map on your right, which is essentially a snapshot of the country. These are data largely provided by the United States Geological Survey and some by the Corps of Engineers and others, which basically we color code just so you can see the level of risk associated with the local communities around the country. There's essentially about 4,000 points there. They're the 4,000 points that we routinely provide service at. If you want to zoom into a particular area of interest, which I have done here on the upper Mississippi and the state of Iowa and Illinois border at Rock Island, you can see along the Mississippi there all these points encoded in purple, which indicates major flooding in that area. And if you click on a particular point, what you pull up is the hydrograph on the right, trying to graphically depict the time evolution of the stage and flow at that particular location. And you can see at that point it was the Mississippi was in recession. The river had crested hours earlier, and stage was declining. We also provide uncertainty information, particularly focused on the long range right now, but expanding into the shorter range in the future, and I'll talk about that. What's available on our website right now is 90-day forecasts of uncertainty information. On your left is a weekly exceedance probability graphic where it shows you the exceedance of the probability of exceedance of various stages or flows for those 1 week periods. And on the right, it's a 90-day aggregate probability of exceedance. There's two simulations. The one in black there is the conditional simulation, which is based upon current conditions. And the one in the blue there, which shows a lower risk, is a climatological simulation, which is simply based upon climatology. In terms of communicating risk, we've had a flood severity, an impact-based 3-tier flood severity scale in practice now for, it's close to over 40 years. And in the scale, essentially, it's an impact-based scale, and we classify the impacts as minor, which may be sort of nuisance flooding or minimal impact, to major, which may mean you have roadways underwater, significant impacts to agriculture, et cetera, et cetera. And recently, there was some legislation passed in this country. It was a Public Law 107-253. It was the Inland Flood and Forecast and Warning System Act of 2002. And in this legislation, there were 5 authorized activities. And one of them basically told the Weather Service that we needed to come up with a new flood severity scale. We need to find a better way of communicating the impacts, of communicating the risks associated with flooding. And what we basically did, we didn't want to just go and just change our flood severity scale because people knew it. We've used it for several years. We invest a lot of time and resources doing outreach and education. In fact, typically over 7,000, we conduct over 7,000 outreach events collectively within the Weather Service each year when you consider all of our forecast offices, our regional centers, and our national headquarters. And so a big investment in time, money, in making people aware in the scale and how to use it. And so, what was proposed to us is to come up with something like the Saffir-Simpson scale for hurricanes, where, those of you I'm sure are familiar with that, which is largely just based on wind speed. And, as we all know, the impacts of flooding are local. 5 feet above flood stage at one particular location is going to have an entirely different impact than 5 feet above flood stage at another location. So we really needed an impact-based scale. We needed a way of better communicating that scale. So what we did is we worked with a number of folks. The Klaus Fornell International, which is a group up in Ann Arbor, Michigan. We conducted no less than 4 American Customer Satisfaction Index surveys, national surveys of our products and services. We work with David Ford Engineering out of the West Coast with emergency managers all over the country to talk about our scale and ways to better communicate it. We did intensive user outreach and focus studies in the state of North Carolina to figure out how we can better communicate this information. And what that all led to is basically inundation mapping, basically graphically depicting where that water is going to be and what the depth of that water is going to be at particular locations. So this is an important partnered activity for us. Again, there's a lot of agencies that are involved in water in this country, and we're working closely with FEMA and the Corps of Engineers, the United States Geological Surveys, state agencies, and others. But the general benefits of this approach are to provide information on the spatial extent and the depth of the water. That tended to be a very important aspect of this for the emergency managers. They didn't want to just know where the water was, but they wanted to know how much. They wanted to make informed decisions about where to pre-position people and resources to most effectively mitigate the impacts of the flood. So this information is very, very valuable to them. And this approach that we employed, working with our partner federal agencies, is really a natural extension of the flood insurance study methodology that's employed by FEMA. Okay, so and it talks about the libraries here. It includes NWS flood severity categories and regulatory FEMA flood categories. We wanted to provide context for emergency managers. They said, how do I relate this to the 100-year flood or the 1% chance flood or the 500-year flood or the 0.2% chance flood? Show me how this all relates, and that's what we're able to do here. The more sophisticated emergency managers just simply download all this information as an additional thematic layer in their GIS, and they've proven to be very valuable. And we've implemented in only 47 locations as a demonstration around the country. And in every single one of those locations, the emergency managers, when they got their hands on these data, we work with the emergency managers to define flood stage and what moderate flooding, what major flooding is based upon impacts in local areas. And invariably, in all 47 of those locations, they changed their definition of flood stage, what stage that occurs, and they changed what moderate flooding was, what stage associated with that, major flooding, et cetera, et cetera. Okay, I talked about education and outreach being important. We talked about a three-pronged approach, or three pillars in the end-to-end forecast process, and education and outreach is really a critical aspect of that. We invest a lot of time and energy with our weather forecast offices, our river forecast centers out of our national and regional headquarters, and going out and communicating people the risks associated with flooding, how to get information, how to use that information. Every year in the spring, the third week of March is National Flood Safety Awareness Week, and we have a campaign where we get out and we try to get with people all over the country to communicate the impacts. We've worked with the American Association of Motor Vehicle Administrators in this country to try to get this message into the driver's license handbook, so everybody who goes to take a driver's license test is aware of the impacts of floods on motorists as well as other weather-related hazards. With regard to water resources, there's a need for expanded information in this country. I talked about water being the new oil. With population growth, economic development, increased habitation and development in flood-prone areas, our vulnerability is going up. Decision makers in all segments of water resources and water management are looking for expanded and new information, higher resolution information, space and time, forecasts of new water resource parameters, and quantification of that certainty at all time scales to more effectively manage the risk. So what are we doing to try to take the next step with our infrastructure to provide that information? We're implementing, with the assistance and close cooperation of Deltari's folks and the engineering firm in the Netherlands, what we call the Community Hydrologic Prediction System, or CHIPS, more affectionately known. It's a flexible, open system architecture which is going to enable us to better share data and information and sort of plug and play and leverage other investments made by other agencies in terms of data and modeling. It's an extension of the flood early warning system and incorporates both models that we currently use now and models produced by the HEC folks and the Corps of Engineers out on the West Coast. Where are we in terms of its implementation? We're conducting parallel operations with our new CHIPS approach versus our old National Weather Service river forecasting system at 4 of our 13 RFCs, and we're going to transition to parallel operations with the other 9 RFCs beginning early next calendar year, and then we're going to completely transition the agency in early 2012. And one of the first major improvements in our services, new pieces of software that we're going to implement, is what we call our HEFS, or Hydrologic Ensemble Forecast System. I mentioned earlier how we provide long-range probability information to try to communicate risk. This is going to provide short through extended range uncertainty information, quantifying the certainty of our forecast, both on the atmospheric and hydrologic end. A lot of the users that we have out there, emergency managers included, want information, particularly in those first 7 days, to better mitigate and manage the risk. I'm almost done. One initiative that we're working on right now with the Corps of Engineers and the United States Geological Survey that we're very excited about is called IRIS, or the Integrated Water Resources Science and Services. And our 3 agencies are coming together and looking for ways to better share data and information, looking at our infrastructures and how to ensure that that we have instant access and ready access to each other's data and information through interoperable databases, data synchronization, so that we can establish in a flood flooding situation a common operating picture for operations. Okay. And my last slide here in terms of where we're going with our vision in the year 2020, we're essentially going to transform our river forecast centers to water resource service centers. Again, there's an expanding need for water resources information out there, to include, gridded high-resolution space and time forecasts of stream flow, soil moisture, temperature, snow water equivalent, et cetera, et cetera, et cetera. There's a real void of that type of information, and to transform our weather forecast offices to water resource extension agents. Really make sure that we have the right people who are trained appropriately to work with local communities and customers and partners to assure that they understand the information, that they optimize its use to manage water most effectively. And that's it. Thank you.
Professor Rafael Oramuno is coming forward now.
Thank you, Paolo, and good afternoon to all of you. I want to share with you this afternoon some thoughts about the flooding problems that we face in Costa Rica, and also why we have had so far a modest success in early warning systems. First of all, I want to show you where Costa Rica is, and this is an important feature because it's located in the equatorial region and more or less between the 8th and 11 degrees northern latitude. And you can see also the position of Costa Rica relative to the Central American region. And because of its geographical position, the Costa Rican territory is constantly subject to flooding problems. And the reason for this is that the country is divided in two big parts, the eastern and the western part, by a main chain of mountains. And these mountains play an important role not only in the runoff pattern, but also in the spatial distribution of the precipitation. This orographic feature, together with the variation of the winds along the year, determines the climate of the Atlantic and the Pacific region. And it clearly defines a pattern of precipitations that are quite different in the Atlantic and in the Pacific region. The trade winds, this is a permanent system that brings humidity to the Atlantic region of Costa Rica. And the low pressure system of the tropical cyclones and the topography of the country, together they couple to bring a lot of precipitation that falls all over the territory, but not in an evenly manner, and that's why we have constant flooding problems, almost with an annual frequency. The floods are typically flash floods, even in the largest basins. We are here talking about times of response that will range from as low as 30 minutes in small basins, up to 12 hours, and probably a little bit more in the largest basin of Costa Rica. Just to give you an idea, the largest basin is about 10% of the total area of the country, and it's about 5,000 square kilometers only. The river length is about 120 kilometers. And in that particular basin, we may have between 12 and 15 hours in the time to peak in the response of the basin. So it's not a very long period of time to issue a warning system. So we can work the alert system from a hydrological point of view. Actually, we need to work it out from a meteorological point of view. And that's my first point here with you this afternoon. But also the system is very dynamic because the problems have increased during the last decade, mainly because of population increase, the development of new agricultural areas, and the increment of the sediment production on the upper parts of the watersheds. And this is also particularly important because Costa Rica is a highly seismic country also. And then, excuse me, we have in the upper part of the basins very steep terrains that with earthquakes they will just lose their balance, and then we lost the forest, the cover, and keep continuously producing sediment that are transported towards the lower part of the basins. Now, just a little discussion on how this system works. The Atlantic region, as I mentioned, is influenced by the trade wind. This is a permanent system of winds. The trade winds will intensify between November and February, and during that time we have flooding problems on the Atlantic region. During the hurricane season, between June and November, the trade winds weaken due to the low pressure systems of the tropical cyclones, but still bring humidity to the Atlantic regions. Therefore, and this is an important part of the characteristics of the country, the Atlantic region does not have a very well-defined dry season. On the Pacific region, on the other hand, it's influenced by the equatorial westerly system. So during the hurricane season, when the trade winds weaken, then the westerly affect the Pacific coast of the country, bringing humidity to this part of the country. Okay? And so in the Pacific, we have a very well-defined season. Now, as I mentioned before, the system is highly dynamic, and the physical characteristics change. For example, on the earthquake of April 1999, there was an uplift of the coast, and then we have changes in the river morphology. And we lost some of the forest and of the natural cover, and now we are still facing, even 20 years later, we are still facing problems, hydrological problems, because of that earthquake. And here is what I mentioned. You can see that's one of the main rivers, the Sixaola River, the Talweg of the river. The scale is distorted. It's about 50 kilometers along the river, and just about 20 on the vertical scale. But as you can see, in the last part of the ridge, we have an adverse slope that now almost all the rivers are facing on the Atlantic coast. And this is more or less how the upper part of the basins look. I just go through these pictures quickly, and this is how it looks on the lower part of the basins. All of the sediment is accumulating in the lower parts. Now, this is the picture. How do we model it? So we need really the scientific part, because it is really a very dynamic and changing system that is continually changing. Due to this interaction between winds, between topography, sediment production, natural cover, we have places, for example, where the main annual precipitation is 1,400 millimeters. We call it the dry part of the country. But 20 kilometers apart, we can have as much as 6,000 millimeters precipitation in a year. So it's a huge and big change of precipitation over very, very short distances, with very steep mountains, with very rapid responses. So this is the picture that we have. And I want also to mention that floods are a major social and economic problem to Costa Rica, and I guess to all our other countries in the world. According to the Central American Committee for Hydraulic Resources, during the period of 1996 and 2001, disasters associated with precipitation represented 84% of all the disasters related to natural hazards. The annual average value of the damages caused by this hydrometeorological event for Costa Rica alone represented 1.15% of its internal gross product. Okay? So now I want just to mention that for the alert systems that we're working on, what we want to do is just to say, okay, We need the alert system, but we will have it on a meteorological basis, and we'll have the emphasis on the short term and the long term. And complemented with that, it must be, and that must is a very important part, it must be an educational program, not only for the people itself, but also on the political level. And in the end, on the engineering level, because also all these alert programs need to be coupled with the infrastructure needed to manage the floods. So, for the design and the implementation of alert systems, we so far put a lot of attention mainly on the information part of the system, because we also do recognize that we do not have a highly dense hydrometeorological network. So usually we tend to think that what we need is information and more data and so more stations, but that is not necessarily true. Remember, we have measurements point-wise. On a station we measure on a point, and we need to distribute that spatially. So we are putting forward the use of satellite systems to be able also to understand how these changes take place in such short distances like these 20 kilometers that I mentioned before. And for the short term, the challenge for the country is to be able to forecast a major precipitation event on small basins with very fast hydrological response at least 12 hours ahead of its occurrence. So, in order to do this, it will be necessary to invest in research, in the meteorological research, to improve the modeling of the weather conditions, just to get the knowledge of what does trigger severe precipitation event over small mountainous drainage basins. But as I mentioned earlier, even perhaps more important is to invest in teaching and education to the people and to the local and national authorities to understand the alert systems and to know what to do when a flooding alarm is triggered. For the long term, the challenge is to devise the social and economic development scenarios that will not compromise or will not be compromised because of floodings, and then planning to achieve those scenarios. That's quite an important part of the whole system, and we need to complement the whole system with the infrastructure needed to manage the floods. This infrastructure has to be focused on long-term investment planning, because we have 34 main basins in Costa Rica. We cannot solve all the problems at once. We will need to see, okay, which one will be the first, what do we do this year, what next year, and that will be probably, I don't know, 25, 50-year long period of investment in flooding management. And this, as we have seen, is a continuous effort, not only because of the investment involved, but also because of the dynamics of the system. So I just want to finish saying that an alert system is a continuous process that is built upon scientific knowledge, but has to be used by society to improve its quality of life by means of planning its social and economic development and minimizing its exposure to risk. Thank you very much.
Thank you very much, Rafael, for this very interesting talk. And a lot of issues were addressed that we can discuss afterwards. Now I would like to give the podium to Professor Tolini, talking about uncertainty.
Thank you, Paolo. Coming here to this conference, I thought that we had to give not a contribution to these open questions. What is risk? Can we measure it? And if we understand it, can we manage it better? But where is risk? I'm talking about flood risk planning and management. I'm talking about flood warning and emergency management, flood detention and diversion, real-time reservoirs management, and related issues. So this morning we saw that risk has a tremendous subjective component, and that is extremely important to be recognized. But formally, officially, risk is defined as vulnerability time hazard, where the vulnerability is somehow related to the impact on elements at stake, and hazard is related to the uncertainty. In general, when we want to assess the vulnerability and hazard, we first have to assess the hazard component. So we start from uncertainty of extreme events, then we pass through rainfall runoff models, the sort of hydrological models that will generate the flow in the main channel. Then through one-dimensional model we will try to assess the flood at specific location, and we will investigate where this flood can go beyond the dikes and flood the area. And at that point we will build two-dimensional models, possibly, to describe the flood inundation, and then put this on top of the vulnerability maps to get the flood risk map. We can see that uncertainty and risk are highly related issues. They're both a combination of the subjective perception of the decision makers and with objective scientific technological analysis and assessment. So I would like to rephrase the questions and say, what is uncertainty? What can we measure it? If we understand it, can we manage it better? Well, generally uncertainty is referred to as a combination of two components, aleatory and epistemic. Aleatory, called also irreducible uncertainty, is the natural randomness of a process, while the epistemic or reducible uncertainty is what comes out from our interpretation, our modeling of this uncertainty. For instance, in the case of an extreme value assessment, the natural variability of it's given by the fact that there is a different probability for different values of flow. But as you can see, we have a large epistemic uncertainty because we don't know if the model we selected is correct. We don't know with the value of the parameters we estimate on a small sample. So we have to take into account the fact that we are not certain of what we are using. But there is another issue that is more important in my opinion, which is the difference between validation and predictive uncertainty. This is not commonly given, but validation uncertainty is somehow related to our models to reproduce the observations. That includes uncertainty in data, uncertainty in boundary conditions, in parameters. But there is another uncertainty, which is predictive uncertainty, and this is the probability of the occurrence of a real future event given the information we have at the moment and given the forecast of our models. In order to understand the role of predictive uncertainty, I will pose the following question. Flooding damages, when they occur, will they be generated by what will happen, or will be generated by what our model is forecasting? Well, it's obvious that these will be generated by the actual future water level overtopping the dikes. So this answer has a very strong implication in the definition of predictive uncertainty, which is obviously the uncertainty of what is going to happen, not of what we predict with our models. We have to consider that our models are avatars, are virtual reality. They are not reality. So predictive uncertainty is the expression of our subjective assessment of the probability of occurrence of a future real event, conditional upon all the knowledge we can gather, data, measurements, models, and after an inferential learning process. Now, just to give you an idea, metrological ensembles, as they are given, are just an expression of validation uncertainty, not of predictive uncertainty, because they express the uncertainty of the model, of the boundary conditions. They are perturbing parameters, they are perturbing boundary conditions. These are not predictive elements of predictive uncertainty. While climatological distribution and extreme values distribution, these are actually predictive uncertainty, although they are not conditional with the last or the latest measurement. This is an example of metrological ensembles generated by the European Centre. You can see the solid line is the observed, the dashed line is what we can do with a model and observe rainfall, and the spaghetti are just the ensemble predicted. You can see that the observed values are mostly out of the ensemble. So if this ensemble was representing your predictive uncertainty, you would expect at least 90–95% of the observation to fall within the ensemble, and this doesn't happen. So let us see what is the definition of validation uncertainty. Is the probability that a predicted value has a specific value given the observations and given the models we are using, given the data. Please know that these can be only used within the time of observations, because observations are not available beyond that time. The use of validation uncertainty is fundamental to improve our models, to analyze how they behave, but it's not usable in prediction. I would like to let you understand what I'm talking about through this graph. This graph represents on one side reality, observed. On the other side, it represents our model forecast. Okay? Now, the validation uncertainty is given by that cut. I have an observation, I have a value, I want to see how my model is spread when the reality assumes the value y star. And this, you have the observation with probability 1. Now, let us go to the predictive uncertainty. It's the probability that a future value of the predictant, the quantity of interest, is equal to a specific value when I know a model forecast. And this is, let us look at it. You see, it's just orthogonal to the previous one. Here, I know the model forecast, because in the future, I don't have measurements. I only have model forecast. Now it's reality that becomes uncertain. And in this case, my model forecast has probability of 1 of occurring, because I have it. So it's a logical development, but it's not easy to make this thing understood by most of the stakeholders. Predictive uncertainty is fundamental when we want to assess expected losses, when we want to assess the probability of overtopping a threshold. Just to give you an idea what we can do, in reservoir management, suppose you have losses described as this sort of quadratic function if the water overtopped the dike. If you have a deterministic forecast, you would say the expected damage is 0, because this is the red line is what you forecast. But if you are in a uncertain forecast, you have a probabilistic description, and now the expected value is not 0, because the function computed in the expected value, when the function is not linear, is not equal to the expected value of the nonlinear function. So just to give you an idea, if we assume linear losses, it's easy to understand how this works. Suppose I forecast this value of overtopping. So in the deterministic case, I would need to release, when I release I lose water, I would need to release that amount just to reach the top of the dike. I'm releasing enough to compensate the quantity. But if I am in an uncertainty environment, I have to release more. And the more they have to release is a function of the uncertainty given by sigma, the spread of my uncertainty, and of a function which is a balance between the cost of water I am losing and the recovery cost I can obtain using the water for different purposes. Let us see a couple of examples where using the predictive uncertainty and marginalizing the predictive uncertainty gives a benefit. The first one is the Aswan Dam. And this case was done many years ago for NOAA because they wanted to improve the forecasting system in Cairo for the inflows to the Aswan Dam. And the question posed to me was, how can we decide that a better flood forecasting system will improve the situation? So by using the information related to the uncertainty, I could prove that, and you can see the blue line on top tells you that if you use this information in developing the operation of the lake, you can benefit of an average of 2.7 billion cubic meter per year, and that is not a lot. It's not a small quantity, it's a lot. The second case is on a Lake Como in northern Italy. And Lake Como, you might know, is famous because George Clooney has his house on Lake Como. But it's a beautiful area, and they had problems of flooding of the city of Como, as well as reduced water. By using this concept of getting the predictive uncertainty and use the predictive uncertainty to estimate the expected damages, we were able to do a couple of things that normally are one against the other. We could reduce the number of flooding. You see there is a number, all the values have been reduced. On top of that, we had an increase of a couple of 100 million cubic meters of water per year and an increase of production of electricity of 3%. So with something very simple, we obtained an important result. I would like to conclude with this example on the Po, which is a flood warning system. And again, if we use a model forecast straight as it is, and we want to decide if we are going to overtop this threshold, you can see that in this point I would say no. But if I use the probability of overtopping the threshold as the triggering mechanism, I obtain a result in terms of decision which closely approaches the reality. This is again the opposite case when I would get a false alarm. It's similar to the previous. You can see that the final objective in this case, by using the model or using the model plus an uncertainty processor that uses the uncertainty or including more than one model, allows you to reduce false alarms and missed alarms. So, concluding, I think that a message that I would like to convey to you is that understanding and assessing predictive uncertainty is fundamental to improve flood management and alleviating flood risk. To do so, models have to be placed, I'm a modeler, but models have to be placed in the right context. They are not reality, they are virtual reality, they are avatars of reality. And we have to look at them as pieces of information that we get to estimate the predictive probability and the predictive uncertainty. Decision makers must trade off what they pay with what they expect to lose, and this expecting to lose is a combination of their own perception of risk and of the predictive uncertainty. The perception of risk is always still fundamental, but because each of them has a different way of looking at it. During normal times, the flood manager will be not risk averse, but when a flood is coming, he will become risk averse, and he will change his way of looking at the problem, and he needs to update in a Bayesian sense his risk and probability. Thank you for your attention.
Thank you very much, Ezio. Now we pass on to our last speaker in this session, Rowan from Willis Reinsurance Company.
Right, thank you. How long have we got? Is it 10 minutes a pop?
Yeah, 10 minutes.
10 minutes.
10, 12 minutes.
10 to 12 minutes, okay. 13, 12, 13?
13, yeah.
Okay. I promise you no more equations, because I'm still bamboozled by the third one. I got the first two, I'm lying, from Ezio. So we're going to talk we will do a little bit of detail, but we're also going to talk a little bit big picture too, about flood. I'm really going to try and explain why, well, we heard from Tom the challenges in the US, which I have to say I felt was somewhat dwarfed by Rafael's challenges in Costa Rica. I'm going to explain perhaps why insurers are particularly concerned about flood. I'm also going to highlight why insurers and reinsurers are particularly, or perhaps even more concerned about flood modelling. And particularly in terms of a big picture, I want to highlight how I think that our sector can have a real role in supporting flood risk management, not just in terms of enabling insurance in developed and developing communities, but also to actually improve and enhance flood modelling and flood understanding. So that's the, and I do have one slide on droughts. Right at the end, so we fulfilled the obligation to those communities. But before I go any further, I just want to clear up a couple of things about insurance, which I've picked up at various drinks do's this week. First of all, insurance isn't just about rich countries. Yes, there's a lot of concern in Europe and North America and Japan, but insurance and insurance companies operate everywhere, and they have to worry about risk everywhere. I have the privilege of having to be responsible for almost every country on earth in my job, and that's about understanding those risks. So let's get rid of this misconception that insurance is just about rich countries. Second thing, let's get rid of this ridiculous misconception that insurance is just about the private sector. It's not. It's about the public sector. In many countries, insurance is arranged through state or parastatal agencies, and particularly in flood, particularly in the United States. So let's get rid of this misconception that it's just about the private sector. And the modelling and the understanding is exactly the same, whether you're sharing risk through insurance or in sharing risk through taxation at local or global scales. And that's one of the grand unifications we need to sort out at this conference. So just as a wrapping up of this little part of the speech, about $200 billion a year $2 trillion a year are spent by communities around the world on non-life insurance. The biggest slug of that is to pay for damages to property from Mother Nature. 10% of all the premiums we all pay around the world go into a global bucket every year called reinsurance. That global bucket is worth about $200 billion a year, and that goes to pay for extreme events wherever they may occur. Floods in the UK, floods in Latin America, or bushfires or droughts wherever they may be. And that money comes from you. It comes from my mother-in-law in northwest Spain. Insurance is the ultimate community product, trumped perhaps only by taxation. Okay? So, there we go. Now on to floods. No more left-wing comments from anyone. I'm bloody pissed off. I'm tired of it all. Right, here we go. This is, you can't see this, but basically this says that there's lots of big events around the world which cost a lot of money to do with floods. It's very painful for governments and insurers, or the hybrids between them, whether you spend $3 billion in Sheffield, or you're in Australia, or you're in Latin America, or wherever you. That's the bad news. Do you remember I said The microphone's working, but the computer isn't. There we go. Right. Remember I said that insurers are really worried about flood models. The reason they're worried about flood models is we don't operate in the real world anymore. We operate in the modelled world. It's sort of an imaginary world. It's Ezio's world. And basically, society around the world is dictated through a kind of convention that the insurance contracts that you buy should tolerate the 1 in 200 year return period. That basically means that 199 out of years to 200, that is to tolerate that event. Now that means that insurance companies have to be capitalized to withstand the maximum probable loss that they could expect once every 200 years. Now there's all sorts of sources of risk for insurance and reinsurance companies. You can have investment crises like we've just had. You can have operational risk crises, which is basically bad management. But here's an interesting, I said there was some detail. This under new European solvency rules for insurance companies, which are mirrored around the world in a kind of a convention. This is a typical solvency capital ratio, the minimum capital that an insurance company should have to withstand that 1 in 200 year event. And basically what it says that underwriting risk, not surprisingly, is the biggest chunk of that. And this sort of medium-sized European insurance company is required to hold 362 million euros of capital to be allowed to write its business. Okay, that's what the models say. Interestingly, catastrophe risk, and this will be from wind and flood, particularly in Europe, unless they're operating in the Mediterranean, where they will have concerns perhaps of earthquake, drives that, and is for the vast majority, $300 million euros of that capital requirement is driven by catastrophe risk. You'll wonder why those don't all add up. It's because you have a correlation benefit or anti-correlation between market and underwriting risk. So there is some method in the madness there. But cat risk is the driver of it all. And remember, we operate in the modelled world. We're lucky enough to have in the audience some cat modelling companies who are absolutely critical to enabling us all to keep our policyholders and shareholders happy. Here's an interesting story. Capital requirement was 362 million euros. We'd have modelled this company, would have taken all its buildings, all its portfolio of houses and assets, and we'd have changed some of the inputs. We'll perhaps know more about the buildings, what they're made of, perhaps a little bit more about the elevation of where they are. And we rerun the models, and actually, suddenly, the capital requirement had been reduced by 57 million euros. That's real money. Modelling is a combat sport. But in 2007, there was a new model released by one of the cat modelling companies that covered the particular region this company had a big portfolio in. Overnight, because of the model change, the capital requirement, and this is the minimum capital requirement, never mind what they should really be operating to be a decent company, raised by 118 million euros. Modelling creates and consumes capital. And there is no more important area of modelling than hydrometeorological modelling in insurance. There is a direct supply chain emerging between public science, cat modelling, capital modelling, and regulatory capital modelling. This is why we have the privilege of working with folks like Ezio and all the rest of it. And this is why it's important. And that's why insurers are getting very concerned and interested about flood modelling. The problem is, it's so bloody difficult. Eskimos, or should I say Inuits, have 20 words for snow. Insurers and the rest of us should probably have 40 words for flood, because the end product is wet carpets. But the cause of those wet carpets are almost limitless. The good news is that trying to confront flood modelling is perhaps the most difficult thing we have to do in our industry. We support more academics involved in flood modelling than any other subsector, and if you add the climate scientists on top of that, it's 2/3 of our academics are dealing with this issue. So the good news is, though, I'm halfway through my career, or maybe a bit more. It'll see me out, and if you've just graduated, it'll see you out as well. This is an endless challenge. It's fantastic, but you've got global climatological drivers and climate change. You've got all sorts of sources of water, from the rivers, from coast, from rainfall, from hail, from subsidence. It falls. Where does it go? River catchments, urban drainage, coastal zones. You've got to worry about the changes in urbanization, whether it's in Costa Rica or in people paving over their front gardens in London to be able to park their cars. It all has an impact. And then there's similar challenges in agriculture and all the rest of it. It's so difficult. Oops. In our industry, you have to worry about the macro scale, this sort of CAP modelling, a portfolio around a country or around a region, and that's what we do in CAP modelling, similar to sort of much of the work we've discussed this week. But then we have individual insurers who are worried about a particular risk in a particular property. That's called sort of the underwriting risk. So there's all sorts of spatial scales having to be mirrored here. River and coastal risk is commonly modelled. We do have storm surge models and we do have standard riverine flood models. But actually intense rainfall models are very poorly, and runoff in cities, really poorly understood. I mean, if you want to ask a big reinsurer who's here, what's their second biggest worry in the US, it may well be convective storm. Because we're just not good at it. Drought, and I will touch on drought, tends to be measured through statistical meteorological indices. Rather than sort of, obviously, the trouble with flood is it has to be measured at such a discrete spatial scale, whereas, someone produced these for me kindly, so here we go. I'm not quite knowing my way around. There we are. We've talked about some of these challenges. What we've got to try and do is integrate sort of global climate modelling stuff, those of us who are in this room in the morning were talking about, try and integrate that sort of mass scale, but downscaled, but then try and integrate that over to local impacts or over larger geographical areas, and whether it's a river basin or even a continent, you have to work at all these different sorts of scales. Trouble is that the water boundaries don't represent political boundaries or insurance boundaries, and it's a pain in the arse. But anyway, perhaps we should just reorganise our geographical boundaries in the insurance world. Just to give you a flavour of how we have to do this technically, you've got to worry about the event set generation. It's perhaps easier when you're just trying to figure out, winds from hurricanes. We have to worry about rainfall data, historic events, then the flow data from flow gauges, and of course flow gauges fail at extreme events, which are the ones we were worried about, the downscaling of models. Then you've got to build a topographical model of the Earth. These are expensive. They don't tend to knit together very well. You can use the space shuttle's free stuff, but that's not very high resolution. But then you do some LiDAR here, and you do a little bit of, you know the idea. Then you've got the models to try and channel that to where does the water go, and then you've got the vulnerability of the built environment, or whatever other assets are being dealt with. Power stations and business interruption. Wind is so much easier. Earthquake is so much easier. Flood is so difficult. Here we go. This is just sort of highlighting that a bit more graphically. I think I'll just sort of skip over that, but we have to worry about where the rain falls and how often, where it correlates. So, I mean, that's quite a lot of Ezio's focus is actually saying, what you've got to try and say is the water isn't all going to fall. You can have extreme events in any particular geographical location, but how likely are those to correlate due to climate systems, antecedent conditions, the pattern and arrangement of river basins? That's one of the reasons that Sheffield had its challenges 3 years ago. So, and ultimately, the vulnerability functions which derive from these elements of water are fraught with uncertainty. No matter where I go in the world, if I ask people in the insurance world what they're most worried about, it's flood. Really, I've asked my colleagues in 3 years ago, what should we do in Latin America? And being a completely ignorant Englishman, I thought they'd talk about earthquake, and it's all about flood. We're currently building flood models in Santiago, Sao Paulo, Bogota, and maybe we start helping out in Costa Rica too. But anyway, I could say the same about South Africa, Southeast Asian cities, Australia, China. Everyone is concerned. Europe, everyone is concerned about this because floods keep happening, but we have precious little understanding of how often that might be. One of the real exciting opportunities is actually better flood modeling for the insurance world in the US, because the US's approach to flood insurance is undergoing some degree of flux. And there are some challenges actually in the current flood. How many is that? 3 minutes to go? There are some challenges in the US, not about flood forecasting, which is what Tom spoke about, but the sort of models that the insurance industry has used in the rest of the world haven't really been developed in the US because there hasn't been the demand, because there hasn't been much private insurance of flood in the US, certainly in the domestic market. There is some commercial lines coverage. These are some of the folks we've been working with to try and begin to build the capacity to deal with this in the US. As I said, with droughts, droughts a little easier because drought operates at a different spatial scale. And here we return pleasantly to our story of global climate models, which are really the key to understanding the distributions of rainfall and extreme events at the sort of scales, both temporal and spatial, that we have to worry about when it comes to drought and agricultural vulnerabilities. I have a feeling, is this my last slide? Yes, it is. There you go. 1 minute to go. I have a feeling that insurance companies and the cat modelling companies who support us are busy building lots of models around the world at different scales because there's an immediate demand. Meanwhile, there's things like the European Flood Directive, which we heard about a bit earlier, which are demanding flood models from other sorts of sectors. But all these things have got to knit together ultimately. One of the interesting things is the only entities that will worry about flood risk at a global scale will be those organisations which have a global portfolio of assets. The only folks who have global portfolios of assets are big insurance companies and reinsurance companies. And they need to manage their portfolios at global scales to diversify them. But critically, remember I said they've also got to underwrite and decide property by property what the price is and what should be insured and what can't be insured. They have to then downscale to different spatial scales. I have a sense that a global sort of flood model will emerge. It will require a variety of counterparties to come together because of this huge complexity. It may not be entirely, it will probably have some similarities in many senses to the global earthquake model that we've heard about. But I'm absolutely convinced that this will happen. And I have a funny feeling that it'll happen even more quickly than some of us dare to imagine. And I dare say it will require a variety of folks in a very big and collaborative tent to make it work. But I think it will happen. Thank you.
Thank you very much, Ron, for your very interesting presentation. Now, could I please ask the panelists to take place here in front of us, so that there are some questions from the audience awaiting them. Okay. There is one question directed at Tom. On the flood maps, regarding the flood maps. So flood maps are great, but are uncertain. How does the NWS use this information effectively, besides just making it available? Yeah, how to, instead of just making available, how to make
Okay. This is a Flood maps are uncertain. How does the National Weather Service use information effectively besides just making it available? Well, essentially everything we provide is we're not clairvoyant, so there's always a certain uncertainty associated with every forecast or warning or anything that we provide, and that includes the flood maps that we partner to generate. What we do to try to assure that they're as accurate as possible is use the best data available, and that, you know, all the sites that we've generated these static flood inundation map libraries at are based upon high resolution DEM, LIDAR data. We have a two-step process that we've developed with the Geological Survey in terms of quality assurance. One based on the output of the H&H analyses, and the second phase of that is really sitting down with the local communities and poring over the historical data that we've compiled from flooding in particular local areas to try to assure the credibility or verify the accuracy of these maps. And we make sure that when our local service hydrologists at all of our weather forecast office or our river forecast centers, they go out and they work with communities, they communicate that there are risks associated with using these data, that there are limitations associated with using these data. They try to convey how these maps are generated and the inherent uncertainties therein. So that's essentially how we deal with that issue. Thank you.
Yeah, then there is a question for Rafael regarding the Costa Rica case. So how do you integrate the whole process of education, science and engineering for risk management in Costa Rica?
Well, I think that's a highly interesting question and also a highly challenging one. I do believe that it is needed integration of the different aspects of flood management and alert systems under one leadership that I also think it should be, at least in Costa Rica, the National Emergency Commission. Because in that way you are going to reduce the need for the emergency attention, and also you are going to reduce the losses due to the emergency or the flooding occurrence. So the way I visualize the whole thing is like having the leadership of the Emergency Commission. You'll take the results that the scientific community is generating at the different universities, and then you pass that to the engineering part for the design. You transform that information into design and into a program that an educational program that can be integrated via the Ministry of Education. Because I think here that the education needs to be on the very basic level, the primary education system and the high schools, but also on the less formal way to communities, like workshops, and particularly at communities in risk. And in that way, I think that the Emergency Commission should work with the Ministry of Education.
Yeah, I have a question for Ezio. In the determination of risk, the concept of return period, that is a technical engineering concept, is still very much used. But how can it be converted, or how can it be communicated or converted into a message that can be used in the area of risk communication?
Well, in a previous session, we had a discussion on the return period concept, and we somehow decided that we will try to fight against it. We will try to abolish the concept of return period and try to find an alternative way of expressing us, because definitely it's too engineering based and it gives the false feeling that it's a deterministic quantity. I generally ask my students, what is the probability of a 10-year return period flood is overtopped in 10 years? And some of them says 1. And it's nonsense. I mean, otherwise you just pose the question, if it didn't happen in 9 years, it is certain that it will happen in the 10th? So this thing is a way of expressing, and I think the role of this conference is exactly this: try to find better ways of telling people what these concepts mean. Yes.
Thank you very much. Then there's another question that came from the audience for Rafael. How do you define priorities in developing flood management schemes in Costa Rica? Where to start? Which criteria are used?
Okay. Well, that's a hard one, and mainly because, as I mentioned, we do have 34 main basins, and at least 25 of them have flooding problems. But I do believe that we may start with the ones where the biggest economical and social developments are. And so I can think about 3 or 4 that right now are very important for the national economy, and also in terms of the population that lives in those floodplains. So I think that and I shall mention those, even though probably most of you won't know the areas, but the Sixaola River Basin in the border between Costa Rica and Panama. That's a very, and I should use the term, explosive region in terms of flooding problem, and even in the equilibrium of the river. Just as a particular joke, the river is the border between Costa Rica and Panama. And sometimes, some mornings, there are Panamanians that are Costa Ricans, and Costa Ricans that are Panamanians because of the shifting of the river back and forth. And so that's a region that needs particular attention. And then the Reventazón River Basin is a very important area for energy production, and is one of the most important basins in the agricultural aspects for the country, as well as the Tempisque River Basin in the northern part, what we call the dry western part of the country, and the Terraba River in the southwest. I think those are like the 4 most important areas, and basically because of their economic and social importance for the country itself.
Thank you very much. Yeah, now I have a question to Rowan and also Ezio, at the same time. Rowan talked. Yeah, you talked about this global hydrological model for sort of GEM type approach for floods. And how confident are we that we can actually calibrate and make this model produce useful results in data poor regions? Because if you extend it to the whole world, we always accustomed to the Western world where we have data, where we have gauges everywhere and so forth. But how can we extend that, extrapolate this sort of modeling to regions like Central America, Caribbean and so forth, where there are lack of data?
Well, I'm going to do the hors d'oeuvres, and then Ezio is going to come in with the main course. I describe a global flood model as nothing more than an aspiration at the moment, but I don't think it's an entirely unlikely prediction that sort of development will emerge. There's certainly plenty of demand for it, if you like, at local and regional scales, and there are some people, as I said, particularly in the insurance and reinsurance world, who would like it at a global scale. So I don't think there's any shortage of aspiration, and certainly GEM has provided a sort of a shining light to say, well, these things can be done. And will it be easy? No, for all the reasons I described. And will it be able to answer all the questions that people want everywhere for a long time? No. But it is something that is extremely exciting to undertake, and it has to be done. And just because it's difficult, we're not sitting here in Washington to do easy things. We're sitting here because everyone I've seen on stage or in the audience are bloody bright, and they're the best at what they do. and collectively we should be able to do this. What's been done in Central America with CAPRA and other initiatives is absolutely remarkable. And so I don't think we should be put off by the challenge, and as I said, at least it'll keep us busy for the rest of our careers. So there we go. Over to Ezio for the main course.
Well, no, it's just that at a different scale it has already happened. Most of the meteorological models, most of the general circulation models at a scale of 100 kilometer or 50 kilometer have already hydrological model built in. We started with ECHAM and the Arno model, then VIC has been used in many of these models. So the concept is there. What is the real problem? At the moment is not data. At the moment is the transfer of information from gauge catchment to engaged units. This is really the problem that we have to face. And there are, I am not saying that it's easy or it's going to be easy, but there are issues that show that if we go at a very small scale, I'm talking less than 1 kilometer, information can be transferred at that scale. It's difficult to transfer information at lumped scale, where we have tried for, I would say, 50 years now, to transfer the pattern or the information on floods from one gauge catchment to another gauge catchment based on lumped characteristics. Now that's not possible because there are phenomena, nonlinear phenomena that come in the aggregation that we do not resolve at the core scale. But if we go at the finer scale, we can. So let's say we will try, we think we can, we will try.
Thank you very much. I think we have reached exactly 4:30. So I would like to thank everybody here, the panelists and the audience, and close the session. Thank you very much.